Hey guys, welcome back to AlgoYogi. We are doing tree series right now. Our next problem in the list is all possible full binary trees. Let's visit the problem on LeetCode. So it says, given an integer n, return a list of possible full binary trees. And we are given n nodes, and the node values for all of the nodes is going to be 0. So no worries there. So now each element of the answer is the root node of one possible tree. So will be basically the list will contain root of each of these unique binary trees, full unique binary trees. Now you may return the list in any order. So a full binary tree is a tree with either 0 or 2 children. We know what a full binary tree is. So we'll be given n, and we are going to basically return a list of root nodes of all the possible full binary trees. So let's say if we are given n equals to 0, then basically the answer would be an empty list, because you can create nothing, basically no full binary trees. Then if n is equal to 1, then we would return just one node. And let's say this is a node, because it's going to have 0 value, so it's not really looking very authentic node, but it is a node. So this is a node. This is what we will return. But what's going to happen if n is equal to 2? In that case, it's not possible, since that wouldn't be a full binary tree. So using 2 nodes, we can either have this node, or we can have this tree or this tree. And these are not full binary trees. These are not full binary trees. So this will basically again return an empty string. So let's see how we're going to approach the problem. We will be basically using a DFS, and the way we are going to compute our full binary tree is, let's choose n equals to 7. Now in that case, what's going to happen is we will have some values, basically 7 zeros from 0 to 6 index. So 3, 4, so 4 and 3, 7. Okay, so it's all about choosing the roots and distributing, basically based on choosing the root, distributing the other remaining zeros or nodes onto either of the side. So since we already have these base cases, so we can basically iterate over choosing from 0 to n, right? And then so it will go to 0 to n minus 1. Since we don't care about the values here, so it doesn't really matter, they will all have zeros. But what's going to happen is we're going to divide given at which index we are. So index is before that value, like before that index, and the values after that index until n, and mainly choosing that particular index as root. We will basically make combinations of those full binary trees we can create, and once that combination is done, so we will get multiple combinations, right? And once that combination basically is returned after returning from the base conditions, then we can assign it to our result array that I didn't talk about it here. But then that is how we will get all the full binary trees combinations. And let's write the solution. All right, let's write our solution. We're going to have an inner function called DFS. So if n is 0, we basically return empty list. That's our return type, and we can't really create with when n is equal to 0. If n is 1, then we return one tree node, that is root with value 0, because that's the only possible value our all full binary tree is going to have. Now we can have result as empty, and then now we're gonna fill it up with all possible full binary trees we can create. So let's have a loop for I in range n. Let's create left trees. So left tree would be coming from calling DFS on basically I, right? And right trees will be coming from calling it on n minus I. Now since we have to utilize one root, so let's subtract one from here, send one less into our right trees. Let me rename it right trees. Now what? Now we're going to use two for loops. So for left in left trees, for right in right trees. Okay, and I think it's going to be the list. So this will return as this tree node. So these are tree nodes, basically left tree node or right tree node. So right trees, I'm calling it right. Now let's append that to our answer. Appending tree node, the value could be it's just 0, so we'll fill in 0, and then we'll provide left and right, and these values will basically for all these they will basically reach to the leaf node, and leaf nodes are basically either just nothing from here or something when the root is 1. All right, so that will be returned, and now what we can do is we can just simply return our result. All right, and then finally we can call our DFS, return DFS on n. Let's zoom out, try to run it on examples. All right, we can submit it. Time limit exceeded, so I think we'll have to use a memoization here, and let's use that. All right, we can have memo would be just a dictionary, and we can have a check if n in memo, we can return memo n. Otherwise we can save for all the n's. Instead of returning here, we can just n equals to result, and I think it does make sense because this is going to call like so many redundant problems, right? As you can see over here, creating this tree is basically redundant because this could be used when it was created. It's like a dynamic problem, right? If this could be created, then why not use the one that we already created at some places, right? If this is created, that means we could utilize it like over here, right? In this next combination that we're trying to make. So I think this might work. So let's try to submit this answer. And yes, it did work. So all right, let's try the time complexity. So time complexity is 2 to the power n, and you can derive it somewhere wherever you like, because this is a little complicated to derive, but I think maybe I'll explain it somewhere later. And space complexity would be n into 2 to the power n, and this is basically coming from stack calls, and this is coming from saving n for each node. We are basically saving all the full binary trees we can create for n. All right, let's go back to AlgoYogi, mark this solved, and see you guys in the next problem. Until then, bye bye.